Hi, it's chemistry time once again, and this time we are going to talk about quantum mechanical model of an atom. So for our objectives, first, use quantum numbers to describe an electron in an atom. Determine the magnetic property of the atom based on its electronic configuration. Draw an orbital diagram to represent the electronic configuration of atoms. So when you say quantum mechanical model, so this model does not define an exact path an electron takes around the nucleus. Rather, it estimates the probability of finding the electron in certain position, at least 90%. So we call it as atomic orbital. So we know that an atom is made up of proton found in the nucleus and electrons are found outside of the nucleus. So how are they arranged outside of the nucleus of an atom is described in the quantum mechanical model. And in the quantum mechanical model of an atom, we need to understand four quantum numbers. So first is the principal quantum number, and this is designated by letter N. So what is this principal quantum number? It defines the total energy of the electron. So it has values of 1, 2, 3, 4, and so on. So this is the first energy level, second energy level, third energy level, fourth energy level, and so on. So the second principal quantum number is the azimuthal quantum number. So this is designated by letter L. So it describes the way the electrons move around the nucleus, or this is the shape of the probability distribution. So the values ranges from 0 to n minus 1. So take note, n is the principal quantum number. So meaning to say, if we have the principal quantum number 1, so the L, its azimuthal quantum number is 0. So we have the S sublevel. So in the second energy level, so since this is 0 to n minus 1, so we have 2 minus 1 is 1. So therefore, we have S-type and P-type in the second energy level. In the third energy level, we have 0, 1, and 2 because 3 minus 1 is 2. So we have the S, the P, and the D sublevels. And since this describes the shape of the probability distribution, so this represents the S orbital. So here, the probability of finding the electron is the same in all directions. The p orbital is a dumbbell-shaped orbital wherein there are three p orbitals. In the d orbital, this is a double dumbbell shape, and there are 5 d orbitals. And the more complicated f orbital, so these are the shapes of the f orbital. So that's the azimuthal quantum number. The third quantum number is the magnetic quantum number, and this is designated by m sub L. So what is this? It defines the possible orientation of the electron in space. And this has a value of negative L through 0 to positive L. That's why if you have in the S sublevel, so its magnetic quantum number is 0. So for the P type, we have 1. So the M sub L is negative 1 to 0 to positive 1. So in the D type, we have 2. It's negative 2 to positive 2. And in the 3 or the F type, it's negative 3 to positive 3. Okay, so again, this is the magnetic quantum number. And the fourth quantum number is the spin quantum number. This is designated by M sub S, where the spin of the electron is either clockwise or counterclockwise, and it has a value of positive 1/2 and negative 1/2. Okay, so if you are to summarize, so in the first energy level, the azimuthal is 0. So the M sub L is also 0. So its spin quantum number is positive 1/2, negative 1/2. So for the second energy level, we have the S and the P, 0, 1. So we have 0, -1, 0, and +1. And this is its M sub S, or the spin quantum number. Okay? So to summarize the principal, the quantum numbers, so the principal quantum number stands for the main energy level. So this is 1, 2, 3, 4, and so on. Number of sublevel is the same with the main energy level. What is the identity of the sublevel? So we have 1s. Number of orbital is 1, and the maximum number of electron is 2. That's +1/2, -1/2. Okay, the spin. And then we have 2, we have 2s and 2p. So we have 4 orbitals here, and the maximum number of electrons are 8. And for 3, we have 3s, 3p, and 3d. Maximum number of orbitals is 9, and the electrons are 18. And for 4, so we have the 4s, 4p, 4d, and 4f. The number of orbitals are 16, and the maximum number of electrons are 32. Okay? So for the designation of the most probable distribution of electron in an atom is called electron configuration. So the quantum numbers that was explained a while ago will be applied in writing an atom's electron configuration. So again, so this is the designation of the most probable distribution of electron in an atom. And in writing the electron configuration, we can make use of 3 rules, or we can apply 3 rules. The first one is the Aufbau principle. So it's a German term meaning building up. Here, electron will successively occupy the available orbitals in order of increasing energy. And in writing electron configuration using Aufbau, we are going to make use of the mnemonic device. So again, this mnemonic will help us check the arrangement of the electron from the lowest energy level down to the highest energy level. So in following this mnemonic device, we'll start with 1s, 2s, then 2p, 3s, 3p, 3d, 4s, 4p, 4d. So 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, 6s, and so on. And take note here, so this will be the s orbital, the p orbital, the d orbital, and the f orbital. Okay? So in writing the electron configuration, you should understand that 1 here stands for the main energy level, or the principal quantum number. Here is the sublevel, the type orbital, which is s, and this one is the number of electron in the orbital. Okay, so say for example, you are to write the electron configuration of this element using the Aufbau. So here in boron, where the atomic number is 5, so its electron is 5. So in writing, we'll start with 1s, following the mnemonic, 1s, 2s, 2p, then 3s, 3p. Okay, so 1 is 2, 2 is 2, then 2p, 1. So if you are to add, we have 5. So this stands for the main energy level, the orbital, and the number of electrons. So the total electrons here is 5. Same as with carbon, so you have 1s2, 2s2, 2p2, and if you add the electrons, there are 6. And also with neon, where the atomic number is 10, so its electron is 10. So we have 1s2, 2s2, 2p6, and if you add the electrons, we have 10. Okay? So if we have chlorine, the atomic number is 17, so there are 17 electrons. How are you going to write? By making use of the mnemonic device. Okay, so we'll end at 3p5. So 1s2, 2s2, 2p6, 3s2, 3p5. And then adding this, there are 17 electrons. So for bromine, which is 35, let's see its electron configuration. So we have up to 4p5. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p, 5, and adding this, we have 35. And of course, for tantalum, where the atomic number is 73, so this is too big. How are we going to write the election configuration using the up-bow? So here, we have up to 5d3. Okay? So adding all the electrons here and following the mnemonic, so the last will be 5d3. So that's how to make use of the up-bow principle. So the next one is Pauli exclusion by Wolfgang Pauli. So here, he emphasized that there will only be 2 electrons per orbital and they are written in opposite spin. Take note of the spin quantum number, positive 1/2 and negative 1/2. So this is how are we going to write the spin in filling the election configuration per orbital. And for Hund's rule of multiplicity by Friedrich Hund, electrons occupy orbitals of equal energy, single first before pairing. So say for example, you have nitrogen where the electron with the atomic number is 7, electron is 7. So this is how are we going to write using the orbital diagram. So since the last here is 2p3, and take note we have 4p, there are 3 orbitals here. So you have to distribute this per singly before pairing. So that is the idea of Hund's rule of multiplicity. Same as with oxygen, where the atomic number is 8. How are we going to distribute this since the last is 2p4? So in writing, single first for the orbital before pairing. So that's Hund's rule of multiplicity. Okay. So another way of writing electronic configuration. So this is actually the shortcut for the up-bow principle. Here, we call it as noble gas electron configuration. So here, why noble gas? Because noble gas is the only family where we consider this family a stable one. Why? Because they have a stable configuration. They have 8 outermost valence electron, of course with the exception of the element helium. And when we are to represent element using noble gas electron configuration, it makes use of a bracketed symbol. So the noble gas is enclosed in bracket. Say for example, how to write the electronic configuration of sulfur, atomic number of 16, using the noble gas configuration. So here, since this is the electron configuration using the up-bow, so we have here 1s2, 2s2, 2p6, 3s2, 3p4, and when we add this, it's equivalent to 16. And the noble gas that we can possibly use is neon, where neon has an atomic number of 10. So this is from 1s2 up to 2p6. So we try to enclose that and then write the rest, which is 3s2, 3p4. So this is the shortcut of the electron configuration for sulfur, and we make use of neon. Okay, we cannot make use of the element argon because argon is 18, so we can't use that. So it's only neon noble gas that is applicable. And for cesium, the atomic number is 55. So this is the electron configuration in up-bow. And here, since if you are going to check xenon, xenon is 54, so up to 5p6. So we enclose that in bracket. So the symbol is used, Xe, and then you write the rest, which is 6s1. So this is a shortcut of writing electron configuration. Okay. Also, in writing electron configuration, we can figure out if an element is paramagnetic or diamagnetic. When we say paramagnetic, it can be attracted to a magnet, or it can be attracted by a magnet. So this is a characteristic of an element that is slightly attracted to a magnet. How? It results from the presence of unpaired electron. Take note a while ago of the Hund's rule of multiplicity, that electrons enter orbital single first before pairing. So with that, the presence of unpaired electron makes the element paramagnetic. Okay? Likewise, the presence of unpaired electron result to diamagnetism. They are diamagnetic. They have no, they are elements without unpaired electrons and it's characterized by non-attraction. So, or even a slight repulsion of an element to a magnet. So, if you are to check this one, say for example, the diamagnetic, you see they are all paired and therefore they have no magnet moment and therefore they are considered diamagnetic. So for the other one, the presence of unpaired electron makes the element paramagnetic. Okay, so these are the examples, where we can check if the element is diamagnetic or paramagnetic. So for sodium, there is one unpaired electron, paramagnetic. We look at magnesium, the electrons are paired, so they are considered, it's considered diamagnetic. And the rest, aluminum, silicon, and phosphorus, are all paramagnetic. Okay? So thank you so much for listening. I hope that you learned something from this discussion.